If you don't already love modeling and similitude problems, by the end of this video you definitely will. The problem on the screen right now with the dam spillway, this is the whole thing. This is the answer. That's it. These are the shortest problems in the entire fluid mechanics course, which means they're basically guaranteed to be on the FE exam because you can complete them in under 2 minutes. Compared to giant conduit flow minor losses problems that take you a half an hour to do, this is a welcome change of pace. You're just checking for geometric similarity, that is, your model and your prototype have the same ratio for all of their dimensions, and then you choose one non-dimensional number, in this case the Froude number, set the model and the prototype equal to each other, and you should be given everything you need. Maybe you have to look something up in a table, but you just plug and chug and find the one unknown that you're looking for. In this case, you see that if you built this experimental model and measured a 3 meters per second velocity, that would correspond to about a 9 meter per second velocity on the actual real world, real scale version of the dam. And that's what makes model studies problems, besides being awesome because they're so short, it's because they're so realistic. This is what engineers actually do. You build scale models and take measurements on them to learn about the real big full-size system before you actually build it. Because it's way cheaper to do it that way than to jump to straight a full-scale model right off the bat. So let's do 3 more example problems. They'll get a little bit more difficult than this one, but not very much. So technically speaking, for dynamic similarity, you actually want all of your non-dimensional numbers, Reynolds number, Froude number, Weber number, Mach number, all of them. You want them all to be equal for both the model and the prototype. Now, a lot of times that's not actually physically possible. You might not be able to come up with a viscosity that matches the Froude number and Reynolds numbers perfectly. So most of the time you just choose one of the non-dimensional numbers to set equal. But in this problem statement, we're given 2. We say that we want to set both the Froude number and the Weber number equal to each other. And the nice thing is that since we're being asked to find the surface tension scale, that means we don't actually have to find a surface tension table to look anything up. Those values, that lowercase sigma in the Weber number, that'll be part of the final answer. We don't actually need to find it on its own. So start off by writing out geometric similarity. We've got a ratio of 15:1, and the prototype is always the bigger one. The model will always be the smaller one. It's a little bit confusing terminology because a lot of times we think of prototype as also being like a model. It's like the practice version, not the full-scale final version. But in this terminology for this problem type, prototype means a final full-scale size. It might not be the actual commercial product, but it's still full-scale prototype. So I start off by setting out Froude number similarity, and the trick to making Froude number similarity easier is to square it. So get rid of the square root in the denominator by squaring everything. It really makes the algebra a lot easier to not have to worry about square roots. All right, now we'll set up Weber number similarity. You probably don't have this equation memorized, nobody does. So just look it up in your textbook or FE exam reference manual. Ultimately, we're trying to find sigma in the Weber number equation, so we probably need to start in the Froude equation and simplify this a little bit. Looks like the easiest progress will be to cross off gravity on the left-hand side. It's in both equations, so we'll get rid of g. If you're not sure exactly where to go, just work backwards, figure out what the final answer is. That's a ratio of surface tensions. So I'm going to rearrange this equation to get those terms by themselves. I'm given that the density scale is 1, so I can cross off the first term and it's like a third of the way done. The geometric scale was given, right, 1 to 15, so I can go ahead and write that part in. And that leaves a ratio of the velocity squared for the model and prototype. And if I look back now over to the Froude equation, there's velocity squared terms over there that I should be able to use. So I can rearrange the Froude equation to get the velocities over each other and see that the ratio of the velocity squared is actually the same as the geometric ratio, 1 over 15. And I can plug that into the right side equation. And you get a ratio of 1 to 225, or about 0.004. All right, Indy's being really loud back here on his wheel. It's really cute and it's awesome to watch, but it's so loud it's hard to record right now. So go ahead and hit the thumbs up if you don't mind watching him for a few seconds until he gets out of his system, quiets down a little bit, and then we'll move on to the next problem. All right, third problem. Probably takes longer to read this problem than to actually solve it. We're given right at the top a 1 to 50 scale for our geometric similarity, so all lengths would be scaled by a factor of 50. And problems with boats in them are sometimes modeled as Reynolds numbers problems if you're dealing with sort of like the aerodynamics of the flow around the boat. But in this case, we're really interested in how the boat causes waves to cause kind of extra flow to disturb the bottom. So this seems very gravity driven and is therefore appropriate for the Froude number. So whenever you see flow through a river or channel or something like that, think Froude number first. Again, I use the squared version of the Froude number instead of the square root version. Can rearrange to solve for velocity of the model, get rid of gravity, plug in all of the other numbers that you know. And you can see that for a 15-knot barge, your water tunnel model only needs to actually be moving about 2 knots. A knot is a nautical mile per hour, with a nautical mile being 2,000 yards or 6,000 feet. So a knot is just slightly faster than 1 mile per hour. And now using the Froude equation one more time, but this time studying the rock that's bouncing along on the bottom of the riverbed, we're given that if we measure 0.15 feet per second for this little moving piece of debris, then on the prototype, a full scale version, that object would be moving at about 1 foot per second. And these all seem like pretty reasonable numbers. This is an actual model that you could really build in a kind of a pretty ordinary lab. Save the most challenging problem for last, but again, it's not that much more difficult. These model studies problems really should be something I want you to be very confident in. When you see it on the FE exam, you should be fist pumping like, yes, I know this one. For this problem, you're asked to find depth and flow rate. And so this is the first time where we weren't actually given the geometric scale, because depth is going to determine how much bigger or smaller it is. So that length ratio is going to be part of the final answer. But we are given a scale for discharge, so given 700 cubic feet per second in the prototype, we can scale that down to find out the volumetric flow rate through the model. It might not be immediately obvious how that even applies, but let's go ahead and just move forward and hopefully it'll fit in somewhere. So dynamic similarity, this is clearly an open channel flow problem, so we're going to use Froude similarity for that instead of Reynolds or Mach or any of the others. I'll use the squared version of the equation, cross off gravity because both of these are going to be built on Earth where gravity is the same. Now, since we're not given any information about velocity directly, we're only given information about flow rate, it may be useful to actually substitute in for these velocity terms. So if volumetric flow rate is velocity times the cross-sectional area of the channel, then for this rectangular channel, we can get that the velocity is equal to the flow rate divided by, I'll call B times D, the base times the depth. So B times D is just area. And your Froude similarity equation now looks like this with a million squared terms all down there. But good news is we have found the final answer we're looking for. We're looking for the depth of the model, which is D sub M. So I'm at a point where I can rearrange the equation to get my final answer isolated by itself. So the ratio of the flow rates are given, so I can square that. I've got LP over LM and BP squared over BM squared. But B is just a length, so I can actually replace B with L because every length has to be the same ratio. B, D, generic L, they're all the same. So I can just put LP over LM cubed now in the equation. So this helps a lot to get rid of some of those terms like the B distance for the model that we didn't know. But now we're kind of stuck in that I don't know DM on the left and I don't know the ratio of L's on the right, but I do know the distance of the prototype, so I could put in that D value. But so we are still left with 2 unknowns. But the trick that I'm going to use to move forward, and this is something that takes kind of a mental leap, it's hard to brute force your way through this, is that the ratio of DM to DP is the same as LM to LP or BM to BP from before. So I can actually combine these D terms with the L terms, and I actually get the ratio of the L's to the 5th power now because I've combined these D squared. And that lets me solve for the geometric similarity ratio, which is a factor of about 9. And so if the model is going to be 9 times smaller than the 4-foot depth of the prototype, then we get a depth in the model is going to be about 0.4 feet. And the good news is that this last problem we did with the flow rate through the channel is probably the hardest model studies and similitude problem that you're likely to see. Having to go back and find the geometric similarity ratio requires a little bit of extra time and a little bit of extra brain power that's not in most problems. So if you were able to follow along with this one, then you should be set. You're really good to go. But if you want one more video just to check and make sure that you're totally solid on similitude, watch this next video that's going to be about drag coefficients and forces. Again, they'll be kind of similar to this last problem, so they'll be kind of challenging, but still probably easier than almost everything else in your fluid mechanics class.